welcome back to the new episode of Who is Who Enzymes. And today I will talk about Villiger Monooxygenases. But before to go into science, I want to jump in the 19th century, where group picture were already a thing. And this was taken in Germany in 1863, and between many prominent chemists that you can see in these images, there is also Adolf von Baeyer and Victor Villiger, and as you can understand, the name of this enzyme comes from them. A few years after this picture, so in 1899, Baeyer and Villiger were working on the cleavage of a cyclic ketone, and they discovered that if they incubate a cyclic ketone with a strong oxidant, so monopersulfate, they could produce the corresponding lactone after 24 hours. This was a starting point of the very known and famous reaction, Baeyer-Villiger oxidation, which is named after the two scientists. And generally, this reaction consists of taking a ketone or a cyclic ketone, incubating with a peroxy acid, and obtaining the ester. So during the year, this reaction was widely used and was also improved, and it could be used with many substrates, also not only ketone but aldehyde. And the two major features are the stereospecificity and the predictable radiochemistry. And also they discovered that if functional groups are it can be also used when there are functional groups present in the substrate. However, there are many drawbacks why this reaction started to kind of stopped to be used, especially for industrial application. And the main thing is that peroxy acids are explosive and very toxic. So this reaction is very environmentally friendly. And also some unwanted oxidation are occurring. So to overcome these problems, we have to jump to the 1967, where Forney and Markowitz, they were studying the degradation pathway of 2,3-decanone in Pseudomonas strains. And they've observed that the major degradation product in the cultivation broth after culture enrichment was 1-decanol. And this was quite surprising for them because they didn't expect such a product. They were more expecting some oxidation of the terminal material. So they postulated that there were some unknown oxidations reaction ongoing in the metabolism of the Pseudomonas strains that they were testing. Just a couple of years later, they identified that the intermediate, the intermediate in the pathway is andecyl acetate. And you can immediately see that this could be the reaction product of a Baeyer-Villiger oxidation of the 2,3-decanol. And they observed that this reaction and this intermediate was present only when they were adding NADPH and oxygen to the reaction. Few years later, in the 70s, another group, they discovered another microorganisms that were capable of a Baeyer-Villiger oxidation, in this case a cyclohexanone to caprolactone. And this reaction is actually one of the most studied, or also, let's say, goal in the field of the Baeyer-Villiger monooxygenases, because caprolactone is the precursor of polymers like also the well-known nylon 6. In this case, it was not a Pseudomonas strain, but as Acinetobacter. And they also observed that they could perform this reaction only in the presence of NADPH and oxygen. So the year later, they managed to isolate the enzyme responsible of this reaction, which they call cyclohexanone oxygenase. And this is the well-known CHMO of nowadays term used for this enzyme short. And so they basically started from nearly 5 gram of protein from the cell-free extract, and after several purification steps, they obtained 9 milligram of pure CHMO. And with this, they immediately did some characterization studies, and they observed that this enzyme was containing flavin. As they observed before, it was NADPH dependent, and it has a very broad substrate scope, which is the main feature of CHMO. Especially for the broad substrate scope and this very attracting reaction, so the Baeyer-Villiger reaction in a much more friendly way. This is started just a chain reaction of many groups that started to investigate on this enzyme, discovering other variant of Baeyer-Villiger monooxygenase, and also try to understand how these enzymes work. So this is the start of our story. And in the next part of the presentation, we will dive between the enzymology, the engineering, and the biocatalysis of these very fascinating enzymes. So the first question that might rise is, so how this enzyme can overcome the main issues that Baeyer-Villiger oxidation has when we are looking at the synthetic, let's say synthetic reaction. So we will look at the catalytic mechanism of this enzyme. As I said before, these Baeyer-Villiger monooxygenases are flavin dependent. So in the first step, NADPH is binding to the enzyme and is reducing reducing the flavin. And the reduced flavin at this step can react with molecular oxygen, and it creates this intermediate, which is called peroxyflavin. And this is, it was identified as the catalytically active species for the Baeyer-Villiger oxidation. So at this point, the important to underline is that this reactive species, it's actually, if it would be in solution, it's quite unstable, but the Baeyer-Villiger monooxygenase can manage to stabilize this for a few minutes. And after that, it can go to the formation of the hydrogen peroxide when a substrate is not present, and this is called the uncoupling reaction. When a suitable substrate is coming into the reaction, a nucleophilic attack of the carbonyl group is happening, and in a concerted manner, we have the formation of a carbon-oxygen bond and the breaking of the oxygen-oxygen bond, and the release of our product. So the product we will have, also in this case, we have a predictable radioisomer. And on the other side, the flavin can pick up a proton. A dehydration step is happening, and we will have the flavin again in an oxidized form. So Baeyer-Villiger oxygenases are actually a very diverse group of enzymes. So many have been discovered. And the main prominent group is the type 1 Baeyer-Villiger monooxygenases, which belong to the class B of flavoprotein. They have NADPH cofactor, and they use FAD in the reaction. Then we have other type of Baeyer-Villiger monooxygenases. Interesting, some, for example, are FMOs. So are enzyme flavin monooxygenases, which are capable of also catalyzing Baeyer-Villiger reaction, like, for example, the human FMO5. And then we have also FMOs type 2 that can catalyze this reaction. And in this case, it's quite interesting because to a certain degree, they can also accept NADH instead of NADPH, which is quite a costly cofactor. So the same class we can visualize in this very nice cladogram where you can see the phylogenetic print with the different characterized Villiger Monooxygenases. And you can see this is the prominent main class, so the type 1 Villiger Monooxygenases. Then here we have the flavin monooxygenases, flavin-containing monooxygenases type 1, the type 2, and then this is groups that are much less representative, so they represented. So the type 2 Villiger Monooxygenases and the type O. So this cladogram is very interesting and very informative, not only for the phylogenetic tree and to see the relation between all the discovered and characterized BVMO, but you can also see the outer ring. It's representing the substrate scope of these enzymes. And you can see that we have enzymes like CHMO, the one very well described and also mentioned before, as a very good substrate scope. So you can really catalyze, so you can accept very diverse compounds. However, you can already see here, so this red bar indicate the thermostability of these enzymes, and CHMO is really at a very, very low stability. On the other side, another very well studied Villiger Monooxygenase is PAMO. And PAMO is a very stable enzyme. You can see that its melting temperature is 60 degrees, but on the other side is a very narrow substrate scope, and especially is not capable to catalyze this, let's say, gold reaction, which is the formation of the caprolactone. Interesting to mention is that Villiger Monooxygenases are also capable to catalyze some, let's say, unconventional, so a bit different reaction. And the most interesting and studied one is the sulfooxidation. And this reaction is studied, for example, also for the biocatalytic synthesis of API, and we will come back later to this. So you can already see from the characterization and the studying of the enzymology and the biochemistry of these enzymes that a lot has to be done on the engineering. Actually, the literature on the engineering on the Villiger Monooxygenases is enormous. Starting from mutating the enzyme to understand their substrate specificity, the feature that gives the stability in PAMO, and for example, also to understand better the catalytic mechanism and the rate limiting step. Cofactor specificity is also a target in the engineering, and this is quite easy to understand. NADPH is a very expensive cofactor, so many groups try to switch to NADH. However, the results were quite, let's say, unsuccessful compared to other type of enzyme when this work was much easier. So this is still the reason also why this is so difficult is still not known. And so if we go much more in details about engineering, again, we have our two main prototype of Villiger Monooxygenases. On one side, CHMO, which is active on a lot of substrate, but not stable. And on the other side, we have PAMO, which is very stable, but is not active on the main interesting reaction for the formation of the caprolactone. So again, there were a lot of studies on trying to understand what are the features in PAMO that can give the stability at high temperature and also in the presence of solvents, and to transfer this feature to the scaffold of CHMO. However, there is no work so far that they were capable to reach the 60 degrees melting temperature of PAMO, but only few degrees of improvement. On the other side, we have a work on engineering work on PAMO, where with direct evolution or computational studies, many groups try to use the PAMO scaffold to perform the oxidation of cyclohexanone to caprolactone. And one example is from the group of Reeds, where they use a technique in a direct evolution called CAST, which is a combinatorial active site saturation mutagenesis. And in this case, from the PAMO wild type, they create a triple mutant that was already observed to have some trace activity on cyclohexanone. And then they target, so they build it three libraries targeting two residues of the active site in each of the library and doing saturation mutagenesis on these residues. And from the best hit of the free library, they started to combine the best mutants and in an iterative manner and started several rounds of mutagenesis to obtain the desired variant. And this is a graph is representing one of the results. And you can see from no activity of the wild type PAMO, they went to some activity, 20% conversion with the triple mutant. And then during different rounds of direct evolution, they obtain, for example, in this case, quite a good conversion of the substrate. And the stars indicate that with this variance, a longer incubation time would lead to 100% conversion. However, you can see that the substrate loading was only 2 millimolar, which is quite far to be industrially applicable. Another example of engineering is done with a very big work from Codexis. And in this case, as I mentioned before, they were interested into a sulfur oxidation reaction. So the product is omeprazole. It's an API in blockbuster drugs used for gastric reflux. And in this case, they combine a Villiger Monooxygenase with a ketoreductase and to perform the sulfur oxidation. So the idea is that the ketoreductase can oxidize IPA to acetone and providing the costly NADPH to the BVMO. So what they observed that there was a wild type BVMO that had some kind of activity with the desired substrate, and then they went through several rounds of direct evolution, created a very vast number of variants to improve the reaction. At the beginning of their engineering work, they mainly focus on the improvement of the productivity, and you can see that after a few rounds, they already managed to improve quite a lot. But however, surprisingly, they actually realized that they were forming the wrong enantiomer. So in the second part of their engineering work, they focus on going back to the right enantiomer and improving the enantioselectivity. And also they wanted to improve the NADP loading. So, and at the end, they managed to obtain only, so they obtain an improvement of under the 40,000. with a 99% EE, and only 0.1 gram per liter of NADP has to be added to the reaction. And we can recall back to the reaction scheme, and you can see that 50 gram per liter of substrate was added. So 0.1 gram of NADP plus is really, it is really low and very good. Okay. So this lead already to the last part of the presentation on the biocatalysis. That was already an example. And BVMO on the mainly were on the biocatalysis point of view, they were trying to be, they were combined with alcohol dehydrogenases, again for the caprolactone production. And these two-step cascade, they were then improved with much more longer and articulate cascades for improving the reaction performance. So why we want to combine alcohol dehydrogenases with Villiger Monooxygenases? So we can start then from the cyclohexanol, and the alcohol dehydrogenase can then provide a substrate to the Villiger Monooxygenase, the cyclohexanone, and also provide the costly NADPH through the oxidation of cyclohexanol to cyclohexanol. When the different groups started to study this reaction cascade, they immediately saw how actually CHMO is, and the overall cascade is inhibited by the product formation. So one idea from the group of Baeyer was to add another enzyme, so the Cal-A from Candida Antarctica, and in this case, to overcome the product inhibition issues, because Candida Antarctica can basically convert the caprolactone to the oligomer product. The other problem is the inhibition when high substrate loading or substrate loading or the cyclohexanol is performed. So their idea was not to add this at the beginning of the reaction, but they did like a feeding of the substrate during the overall time of the 48 hours. And in this way, they managed to have a 99% conversion of 200 millimolar of cyclohexanol. And when they looked at the product, they realized that they had 75% of the oligomer and then 25% of still the lactone form. Then again, on this reaction, Albers and Freie, they try to create the fusions of the two enzymes, and they compare with the addition of each of the ADH and the CHMO individually in the one-pot reaction. This is the best fusion variant that they obtain, and they compare, as you see, with the two enzymes combination added individually, and the improvement is quite impressive. So they got a 99% conversion, while when you had just the two enzymes individually, you have 42%, and you can see also the turnover number is drastically increasing. Also in this case, they follow the idea of Baeyer, and they had Cal-A lipase in the reaction mixture, and they also perform a substrate feeding of cyclohexanol during the entire reaction. Another example of cascade, in this case, is a cascade that is defined in a convergent fashion. And this comes from the group of Selinkara. And in this case, we have the addition of the cyclohexanone, and then in the 1,6-hexanediol. And this was done in a ratio of 2 equivalent of cyclohexanone and 1 equivalent of 1,6-hexanediol. And in this case, then they have an ADH that is converting the hexanediol in the caprolactone, and meanwhile providing the NADPH for the BVMO, and which can then transform the cyclohexanone to the caprolactone. Also in this case, they test different BVMO combined with the different ADHs, and again, they saw that the best conversion was with the CHMO combined with this TES ADH. When they scale up the reaction to 50 milliliter, they obtain a 99% conversion based on the cyclohexanone and with 20 millimolar product formation. So with these examples, I already come to the end of my presentation and the conclusion. So Villiger Monooxygenases are quite intriguing and fascinating enzymes. And this is also, I think, proved by the enormous amount of literature that I found, which of course, I couldn't present everything. So if you are much more interested, I really recommend to went through reviews and papers because there are many other examples. They perform a quite demanding reaction with quite control selectivity. However, although the information that we have is very good and deeply understood, we are still not, we still didn't finish. There is more to understand. For example, as I say, the reason why some enzymes are stable and others not, or why some enzymes, for example, accept a different substrate or other. So there is still a lot of work for many PhD and student and postdoc to come and grant to write. And also there is still a lot of work to go towards industrial processes that they will come, but there is a few steps that biocatalysis group can work on, like as I mentioned, the operational stability of the enzymes, the switching to an NADH, for example, switching also to an NADH dependent enzymes, or creating a self-sufficient enzyme that then you don't have to rely on a recycling system. With this, I would like to conclude my presentation and say thank you for your attention. And if there is any question, I will try to answer.